Dear students, now that we have some idea about support vector machines, in this lecture we will talk about specific constraints that would help us formulate SVM as an optimization problem. Now in our last lecture, we learned that in most of the cases, the function of our classifier is to locate our decision boundary in such a way that it is that the farthest distance possible from some of the positive samples we have and some negative samples we have. So if R is the magnitude of the first sample that we are encountering as a positive or vice versa as negative, we want to maximize this separation R. But how we should come up with the closed form equations or certain optimization relationships that we can solve. So we will consider a simple two-dimensional example. Let us say that we have origin here, and from origin we join this particular origin to the positive vector represented by XA. So if this is our XA, we already derived that whatever weight vectors that we are going to talk about, weight vectors are going to be orthogonal to our hyperplane. And if we take the projection of this first vector XA on hyperplane, we can write this as XA dash. Now, one thing is for sure that the direction of R can easily be obtained by the unit vector in the direction of W, because if we are talking about the shortest distance, that has to be orthogonal, and we have derived that since this is orthogonal, all the lines that are orthogonal to the hyperplane, they should be parallel to W. And to derive the direction of unit vector, we can simply take vector W and divide it by its norm so that it becomes a vector of unit length. That would imply that using simple vector addition, we can also say that this XA equal to XA prime plus R times W vector divided by norm of W, which would imply that XA prime equal to XA minus R times W vector divided by prime of W. So this is first condition that we have derived using simple geometrical representation and using vector addition and vector subtraction. Now let us make an assumption. So this assumption would help us take care of the scales, because X could be in a different units, weights could be in different units. So what we will do, we will define all the distances, because we said that we have to maximize certain distance R. So what should be the unit of this distance? Should we follow the units of our X, or should we follow the units of our weights? So we will say that everything would be working in the units of hyperplane, and one assumption that we are going to make is that, let us say that the first vector that is classified as positive or negative in otherwise is at distance 1 from the hyperplane. So that would mean that if equation of hyperplane is represented by fx, that fxa should be equal to 1 if we are talking about unit distance, which would imply that for first point we can write it as wxa, their dot product, plus b should be equal to 1 when ya is equal to plus 1. Likewise, we can write for the negative side that if it is represented by vector xb plus b equal to minus 1, if yb equal to minus 1. As we did in previous case, we can combine this to write a general equation that y should be w times x, their inner product, plus b equal to 1, and this y plus 1 minus 1 will always take care of the sign. And this is only applicable to the first vector that we are encountering on either side of the hyperplane. Now there would be many more points, some positive points here, some negative points here. So it is pretty clear that for all other points which are not forming these vectors that are giving us support, hence the name support vectors, we can generally write that for all other vectors, wx plus b should be greater than equal to 1, and wx plus b should be less than equal to minus 1. And we are saying this is for the case when y is positive, and this is for the case when y is negative. And we can combine these two relationships into a single equation, which we can write as yn w xn, their inner product, plus b greater than equal to 1 for all the samples n equal to 1 to how many samples we have depending upon size of our training data. Now, since we are talking about training data sets time and again, we are essentially dealing with the supervised learning approach. That means we will use some training data that is already available to us to come up with the decision about this partitioning hyperplanes and hence determine the optimal location of that particular boundary. Now, if this is clear, we have come up with two good relationships. One is this constraint should always be satisfied. Another is we have calculated what this xa prime would be, which is xa minus rw w bar. Also, we would know that if we take the projection of xa on xa prime, that should lie on fx equal to 0, and that implies that f of xa prime should also be equal to 0. If we substitute the value of xa prime that we wrote before, which was xa minus r w upon w norm, we can simply write this expression as w times xa minus r w upon norm of weights, their inner product, plus b equal to 0. Now, with the assumption of this bilinearity of inner product, we can clearly write this as w times xa plus b minus r w times w divided by weight vector equal to 0. Now, if you see that we started with the assumption that this has to be 1 because this is the equation of wxa plus b or fx equal to 1. So this is the value, would take the value of 1. This would be r w upon norm of weight vector, which is equal to 0, which implies r can be written as weight, norm of weight divided by inner product of w and w. And we know that this inner product of w and w by definition is square of the norm, which can be written as w square, which implies that r is given by w norm. So that would mean that if we want to maximize the r, we have to minimize the norm of the weights. And we can also write this is that, so this is our maximization problem. So we can also write this as, if we have to maximize 1 upon w, that is equivalent to saying that we want to minimize w. Also, this is equivalent to say that we want to minimize w square. And for ease of mathematics, if you know basic optimization, if you multiply a particular constraint by a positive constant, the sign is not going to change. So we can say that this is equivalent to minimize half w square, and the reason we write this in a form because it guarantees us the convex form of the objective function. And now this is subjected to the constraint of yn w xn plus b greater than equal to 1 for n equal to 1 to n. And now we will focus on solving this particular constraints and get our solution. But one thing again that I would highlight is that this is the hard margin. There is an assumption that all the points are linearly separable. Only then these constraints are going to satisfy. So for example, if we consider in figure A, you can clearly see that we can declare this as support vector. We can declare this as support vector and find the optimal location of our hyperplane that maximizes R. On the other hand, we would have some data sets where there is no way we can draw a linear separable hyperplane that can give us a perfect partition. So for all these points, this constraint of yn w xn plus b greater than 1 is going to be violated, and we would never have a feasible solution based on the constraints that we just outlined. And that's why this is called as a hard margin problem. So what we should do, we need to allow for some laxity. We need to make these hard margins as the soft margins, which would be our topic of discussions in next video. Now, just a quick recap. If you clearly look here, although this math looks intimidating, this just relies on the basic vector addition and an assumption that we make regarding the first location of a point, which we also call as the support vector. But once you start using support vector machines in your research, this maths is something that you have to always face with, and that's why this is indispensable even in an applied course. Thank you.